Good morning. I welcome you to another opportunity to learn with the Chidons Academy. I'm Pharmacology Daniel, popularly known as Pharm Chidons. This morning, we will be discussing pharmacokinetics of drugs. But before we proceed, what is pharmacology, you may ask? Pharmacology is derived from two Greek words, pharmakon and logia. Pharmakon meaning drug or poison, logia meaning study of knowledge or knowledge of. That is to say, pharmacology entails study of drugs, its action on the body and the body's response to it. Or putting it another way, pharmacology entails study of drugs, its interaction with molecules in the body and body's response. This pharmacology we are discussing this morning is broadly divided into two. One, pharmacokinetics, and two, pharmacodynamics. When we are talking about pharmacokinetics of drug, it simply means we are studying what the body does to the drug. Then when we are talking about pharmacodynamics of drug, it simply means the study of what the drug does to the body. Now, in today's topic, we'll be discussing pharmacokinetics in full. Pharmacokinetics, as we said, simply means study of what the body does to the drug. It simply also entails the description of a drug exposure by characterizing ADME as a function of time. I said by characterizing ADME as a function of time. You can also say that it describes a drug exposure by characterizing LADME as a function of time. Why do we talk about LADME? L here means liberation, A means absorption, D means distribution, M means metabolism, E means excretion. We talk about LADME or this L, we include this L when we talk about some dosage forms such as oral drugs, tablets, capsules. When a tablet or a capsule is taken into the body, it will not start working immediately. It must get broken down, get dissolved. After getting dissolved, what will happen now is that the active pharmaceutical ingredients will get liberated from that formulation, then get absorbed. Now, because the active pharmaceutical ingredient called API should or must get liberated, it simply means that we must include liberation when we talk about oral dosage forms. Now, as I said, A means absorption, D means distribution, M means metabolism, and E means excretion. When you want to talk about metabolism and excretion, metabolism plus excretion is equal to elimination. So, metabolism and excretion gives rise to elimination. Then, distribution, metabolism, and excretion gives rise to disposition. The implication is that if we want to call distribution, metabolism, and excretion together, you use the term disposition. Now, there are two major rules of drug administration, and one of it is intravascular routes. One of it is intravascular routes, the second is extravascular routes. What is intravascular route? Intravascular route is limited to only intravenous and intraarterial, whereas extravascular route is for every other route outside these two routes just mentioned. That is, extravascular routes are for oral, taken through the mouth, subcutaneous, through under the skin, then sublingual, intraperitoneal, intrathecal, and others. Now, these two major routes of drug administration have a graph. Look at the one of for intravascular routes. Then look at the one of intravascular routes goes this way. The one of extravascular routes goes this way. This is for extravascular routes. Now, this intravascular route has this to be the level of it. Here is elimination. Here is distribution. While this extravascular route has this level: absorption, distribution, and elimination. From these two graphs we just sketched, you will notice that for the intravascular route, that is for the one of intraarterial and the intravenous, you will notice that it has distribution and elimination only. It does not have absorption phase. But extravascular route, that is for oral, intramuscular, intraperitoneal, and others, for this extravascular route, they have absorption phase, distribution phase, and elimination phase. That is to say, there is one difference between these two graphs. One is that intravascular route does not have absorption. What do we mean by this statement? It simply means that when a drug is given through IV or IA, intravenous or intraarterial, that is through the vein or through the artery, the implication is that that drug will go straight into the systemic circulation, into the bloodstream. That drug will not start following the process of absorption. It will go straight and get distributed. So the only thing that happens to that drug is distribution and elimination. And that is why, since we know that the drug will bypass absorption phase, since it will bypass it, the implication is that you have to be very careful with the drug you are given through IV. Ensure that the drug is very sterile. Ensure that the drug is free from pathogenic organisms, free from particulate matter. Now, if you are not well trained medical personnel, please don't give through IV before you cause problem to the patients. Now, if you are giving drug through IV, ensure that you insert the needle at an angle of 15 degrees so as not to burst the person's blood vessels. Because once you burst the person's blood vessels, the person may not forgive you in his life. So don't risk the life of your patients. Now, we have seen that intravascular route does not have absorption phase. Okay? Now, we go to extravascular route so that we can learn more on it. In extravascular route, we say it has absorption, distribution, and elimination. Let's draw the curve so that you see it very well. Look at the curve. Now, this point is called the peak concentration. This point is called peak concentration or maximum concentration. So we call it Tmax. Why this point is called Tmax? That is the time it takes the drug to get to the maximum concentration. Then, as you have gotten Tmax and Tmax, when from here to here, the absorption will be more than elimination. Absorption more than elimination. Now from here to here, elimination more than absorption. Then from here, if we have this point, maybe here is 1, 0, 1, 2, 3, 4, 5, 6, 7, for instance. If this point is called the minimum effective concentration. The minimum effective concentration. This simply means that if the concentration of the drug, remember this y-axis is called the concentration axis, while this is called the time axis. Now, the implication for this minimum effective concentration is that if the concentration of that drug is below this minimum concentration, that is less than minimum effective concentration, it means that the concentration will be called subtherapeutic concentration. Now, we call this point subtherapeutic concentration. Subtherapeutic count. So, it will not be able, the concentration will not be able to elicit pharmacological or therapeutic effects. Then, the point here is called minimum safe concentration, maximum safe concentration, or minimum toxic concentration. Remember, maximum safe concentration or minimum toxic concentration. The implication of this is that once the concentration of the drug is above this range, is around this side, the implication is that that drug, the concentration of that drug will be very toxic to the body. But once it is below the maximum safe concentration, the drug is very good. That is why we say from here to here is called therapeutic range. Now, since this point is called minimum effective concentration, the implication is that this point is called the onset of action. Onset of action. While this point is called the termination of action. Here, termination of action. Here, onset of action. That is to say, from here to here is called duration of an action, or duration of action of the drug. Okay, so these are typical things that happen in extravascular route graph. Okay, now we want to define terms, since we say that pharmacokinetics involves the study of ADME. Let's see definition of terms. One, ADME. We say ADME. The first term we want to discuss or define is absorption. Absorption simply means the movement of drug from site of administration to the site of measurement. Remember, intravascular routes of administration do not have absorption phase. It's only extravascular routes of administration. Now, measurement of a concentration of drug is usually done through the plasma or the blood. So it's only through the blood or the plasma that you get the concentration of the blood, the drug in the body. Then distribution. When we talk about distribution, once a drug is absorbed, the blood carries the drug to organs of the body. Now, the distribution of a drug around the organs of the body is dependent on some factors. One, it depends on how perfused the organs are to the blood. It also depends on the organ size. It also depends on the binding of the drug to the tissues. Now, we'll talk about metabolism and excretion, which we said that the two are called elimination. What does metabolism mean? This simply means the conversion of a drug or the conversion of chemical from one chemical species to another. Then, when we talk about excretion, this simply means the irreversible removal of unaltered drug or unchanged drug from the body. Now, these two, we said they are called elimination process. That is, elimination process are metabolism and excretion. Now, there are two major organs used for elimination of drug. One is the liver, two is the kidney. Other organs are the lungs, which is used for volatile substances and which is also used for gaseous anesthesis. So volatile substances or gaseous substances are what the lungs eliminates. Then, when we talk about kidney, the kidney is used for excretion of drugs and it's also used for metabolism of some certain drugs. Yes. Now, when we talk about the liver is known as the usual organ for drug metabolism. Yes. Now, when a drug has a narrow therapeutic window, so to speak, it simply means that that drug will be eliminated rapidly. And so, small doses of that drug must be given often to achieve therapeutic effect. What do we mean? Take, for instance, oxytocin. Oxytocin is known to have narrow therapeutic window, and so it's eliminated within minutes. And so, small doses of this oxytocin have to be infused at a precise and constant rate through IV infusion in order to achieve therapeutic effect. Now, we want to see some questions on this pharmacokinetics. There are many pharmacokinetics parameters we have, and one of it is elimination rate constant. The second one is biological half-life. The third one is apparent volume of distribution, and the fourth one is area under curve. Let's see how we can get the answers to these parameters. Let's see the question on the board. In the question we have, it said the plasma concentrations after the 250 milligram intravenous bolus dose of an antibiotic is given below. Plot the graph, plot the data, and describe the pharmacokinetic model. And we see the time, we see the concentration. For you to plot the graph of pharmacokinetics, you have to use semi-log graph. Look at the sketch of semi-log graph. As you can see in this graph, it's quite different from the normal graph you know. Here is bigger than here, here is bigger than here, here is bigger than here. Like that, it keeps reducing. We call it semi-log graph because one of its axes, maybe the y-axis as you can see here, is in logarithm in base 10. And that is why the value or the number you are to put on this graph must be a logarithm in base 10. What do we mean? If here is 0.1, here must be 0.1 times 1, 0.1 times 10, please. It will get 1. Then 1 times 10, 10. 10 times 10, 100. This is concentration axis, conc axis, which is a microgram per mil. While this is time axis, and which is an hour. So, while plotting this graph, we call it semi-log graph. That does not mean that you will put logarithm on this y-axis, or maybe say log of concentration. No. The implication is that this graph is already in logarithm form. So what you know that you don't need to put log concentration here anymore. Now, let's plot the graph. Now, here is 1 for time axis. 1 against, now see how you read the graph. If here is 0.2, if here is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. Then 2, 3, 4, 5, 6, 7, 8, 9, then 10, 11. When you have 10 here, what you now start, because here is 100, say 20, 30, 40, 50, 60, 70, 80, 90, 100. Now, what it simply means is that now, already this is already in log form. Now, see what you do. You say, this time 1, you plot it against concentration 8. Let's get the 8 from concentration axis. Here is 1, 2, 3, 4, 5, 6, 7, 8. It means that it will be located here. Then 2 against 6.3. This is time 2. 6.3 will be, here is 1, 2, 3, 4, 5, 6. 6.3 will be in between. Then we talk about 3 and 4.9. Here is 3. Now, 4.9 for the concentration axis will be, here is 2, 3, 4. 4.9 will be around here. Then 4 against 4. 4. Here is 1, 2, 3, 4. Here is 4. Then 5 against 3.2. 5 against 3.2. Here is 1, 2, 3. So here is 3.2. Then 6 against 2.5. 6 against 2.2. 2.5 is here. Then 7 against 1.9. 7 against 1.9 is here. You can see we have gotten the graph. Then what happens now is we want to get the value for these pharmacokinetic parameters we are talking about. Now, the highest point of this graph is what we call the C mass, which is noted as CO. So this point is called the C mass, which is called CO. Then, now, we want to see how we can get the pharmacokinetics parameter. 1, elimination rate constant. How do we get it? If you watch this graph, you will notice that as the concentration increases, here we say is elimination phase. Elimination phase. So, if you look at this graph, you will notice that as concentration increases, the elimination rate increases. If the concentration come down to this, if the elimination come down to this, the concentration will reduce. If the elimination come down to this, the concentration will reduce. So because the higher the concentration, the higher the elimination rate. We say that this graph obeys first order reaction equation. What does first order reaction equation state? Let's see the formula. It stated that the concentration T equals to the peak concentration minus KT. Now in logarithm form, it says that log concentration T is equal to log CO minus KT all over 2.303. From this equation, you will notice that once this comes to the other side, it will turn to log Ct minus log Co equal to minus square T over 2.303. We have this minus. That is why this graph is in negative form. Now, once this T comes to the other side, because this equation simply implies that when you plot the graph of logarithm concentration time against T, this will be the intercept on the y-axis or on the vertical axis, while the totality of this will be the what? Slope. When you plot the graph of log Ct against T, the implication is that log Co will be the intercept on the y-axis or vertical axis, y minus square over 2.303 will be the slope. That tells us that when you say log Ct minus log Co all over T will be equal to minus square all over 2.303. That tells you that this is your slope and is equal to this, where the K is called elimination rate constant. Now let's see how to get the slope. This point, this highest point, is your CO. You say CO is equal to 10. Then this lower point here, 2, is your CT. You say is equal to 2. Now, this is 10 microgram per ml, while this is 2 microgram per ml. Now, because we have the formula to be log Ct minus log Co all over T, note also that this point is in first T, T2 equal to 7, while this point is T1 equal to 0. Now, we plug them into this formula. It will be giving you log what is our Ct? 2 minus log 10 all over T. This change in T will be 7 minus 0, 7. That will be equal to minus square all over 2.303. Now, if we compute this will be giving you, this implies log 2 minus log 10 will be giving you log 5, that log 1 over 5 from subtraction law of logarithm. Log 2 minus log 10 will be giving you log 2 all over 10 all over 7 equals to log 1 over 5 all over 7. Now, log 1 over 5 will be giving you, let's clean the board. So, it will be giving you minus log 1 over 5 all over 7 will be giving you minus 0.09985 per hour. So, this will be taken to be the slope. And remember that the slope we just got is equal to minus square over 2.303. The implication is that we will equate the slope, which is minus 0.09985 per hour. We equate it to minus square elimination all over 2.303. From here, minus will cancel minus. And when minus cancel minus, it will give you that K elimination will be equal to cross multiply. This times this will be giving you 0.2299 per hour. So, the K elimination is equivalent to 0.2299 per hour. Do you understand it? Now, we go to half-life or biological half-life of this drug. Why do we call it biological half-life? It's because we have different types of half-life. We have effective half-life, we have physical half-life, then we have biological half-life. And this biological half-life we talk about simply means because we have to get the time it will take for 50% of this drug to get eliminated from the body. Because we are talking about what happened in the body, we call it biological half-life. Now, let's see how to get it. You can get it from your graph. Remember, the maximum concentration of this graph is 10. Half of 10 is 5. This here is 2, 3, 4, 5. So 5 is half of this 10. If we trace this 5 to this line, if we trace this 5 to this line and trace it to x-axis, it will fall at 3. That tells us that the half-life of the drug is approximately to be 3 hours. Half-life equal to 3 hours. That is from the graph. Now, if you don't want to use graph to get it, you can get it from a formula. Now, since this pharmacokinetics obey first order equation, reaction equation, the implication is that you use the formula half-life equal to 0.693 all over K elimination. And what is K elimination? That is this. It will be 0.2299 all over 0.693 all over 0.2299. If we divide this with your calculator, it will be giving you 3.01 hour. This 3.01 hour is same thing with 3 hours. This is for formula method and this is from graphical method. We have gotten two pharmacokinetics parameters called elimination rate constant and biological half-life. Now we want to get the apparent volume of distribution. Yes, to get apparent volume of distribution of the question we are discussing, we say apparent volume of distribution known as VD is equal to the dose of the drug all over the C mass. What is our dose? From the question, it says 250 milligram intravenous volume. That is, 250 milligram is the dose. We say 250 milligram. We say 250 milligram all over. What is our C mass? Is 10 microgram per ml. Now, you don't divide. Why? Because they are not in the same unit. If you divide it this way, you'll be very wrong. Now, ensure that this milligram is in microgram. Now, look at the equivalence. 250 milligram over 10 microgram per ml simply means 250 microgram all over 10 microgram per liter. Now, here is the microgram, here is the microgram. Now, when you divide now, because you can now divide, they are in the same unit. When you now divide, what you'll be getting is that volume of distribution is equal to 25 liters. Do you understand it? Now, we want to do the last one, area under curve. To get the area under curve of this graph, what does area under curve mean? This simply means this region bounded by this graph. Area under curve. There are many ways you can get area under curve. You can use trapezoidal rule. You can use method of cutting and weighing. You can use method of counting squares. You can also use formula methods. Now, what do we mean by this trapezoidal rule, triangular rule? This simply means application of mathematics. Like, look at this shape. Do you know that we can extend this graph? So when you extend it to the x-axis or horizontal axis, you have this. Now, this gives you a shape of a triangle. And remember, from our primary school time, we were told that area of a triangle simply means half times base times height. Here is the base, here is the height, here is the base, here is the height. So we say area equal to half times base times height. What you knew from your primary school time. Now, how do we apply this? From here is 0. When you see something packaged like this, here is S Cartesian axis or horizontal Cartesian axis, and here is Y. Here I mean, for the Y axis, you start from 1, 2, 3. For the S axis, you start from 0, 1, 2, 3. Now, the region from here to here will be your base. And that will be, here is 9, here will be around 9.6. You say 9.6. Then, from here to here is 1, and here is 10. 10 minus 1, 9. You say here is 9. So our base is B, and our height is 9. You say equal to 1 over 2 times 9 times 9.6. That will be giving you 43.2 microgram hour per mil. Please mind your unit. Now, another way you can get this area is by using the formula area under curve equals to the maximum concentration all over elimination rate. Our maximum concentration is 10 from our graph, maximum concentration. Elimination rate is 0.2299. And when you compute this, it will give you 43.5 microgram hour per mil. So they give a close answer. Now, we have seen from our calculation that the dose of the drug is 250. That is the dose of the drug administered. Now, after administering this drug, we realize that volume of distribution is 25 liters. Then we also realize that the elimination rate constant for the drug is 0.2299 per hour. We also realize that the area under this curve is equal to 43.5 microgram hour per mil. Then we also realize that the biological half-life of the drug is approximately to be 3 hours. These are the values of the pharmacokinetic parameters we have. Hope you enjoy it. Thanks for watching the video. Please don't forget to turn on your notification button, and please don't forget to click subscribe. Stay safe. See you next time. Thank you.